as well. The project itself, it has multiple work packages, and it's focused, the big picture is really focused on trying to develop different kind of sensing technologies or use sensing technologies in order to support all kind of movements or infrastructure mobilities or things of that nature in colder climate regions and specifically remote regions such as Arctic regions. Before I move any further, I should acknowledge a number of people who have played very critical role in this project. Adam Hunsaker is a research engineer who's been working with us since the start of this project, and you can actually see Adam in the picture. They're all bundled up because we were out there doing some testing in sub-zero conditions. Professor Jennifer Jacobs and Professor Mike Pallas. Jennifer Jacobs, she's a professor with joint appointment in civil engineering and in Earth and Ocean Sciences Department. She is the lead for the overall project that we have, and then the work package that deals with infrastructure. I'm leading that effort. Dr. Mike Pallas, he's a director of what we informally call the Drones Lab on our campus. He was one of the early adopters of this technology. He's also from Earth and Ocean Sciences Department, and he's our go-to person for everything related to drones and technology there. I should also acknowledge three people directly related to the project. Dr. Eli Deeb is the technical point of contact on the overall project for infrastructure tasks that I'm talking about here and that I'm leading. Chris DiCarlo is the specific task lead on that. And also Dr. Sarah Kobzinski, who is the contracting officer's representative, who helps us out with all sorts of administrative topics and also keeps check of all the progress on project and so on. So now that we have had some introduction on the project itself, what I'm talking about here in today's presentation is to try to come up with a method or a platform that people or agencies can adopt in order to determine or detect when there's formation of black ice on the highways or roadways in general. So before I go any further, I should describe what I mean by black ice. Black ice is typically a thin layer of clear ice, and clear being the key word there. That's why it's so dangerous, because it's very hard to detect when it's present. You're oftentimes not able to realize it. In daylight, it's somewhat easier, but especially at night, it's very difficult to identify it. So it's usually a sub-millimeter thick, thin layer of clear ice on your roadways that forms during inclement weather conditions. And a big challenge with that is, due to presence of this ice layer, there's a tremendous loss of friction on your pavement surface, leading to not only the loss of braking effort, but also loss of tractive effort. So when vehicles are trying to move, they really have challenges with that. And I'll just give a very simple example of myself from year 2002. I will never forget us coming back from Chicago and trying to take the interchange that goes from Interstate 57 to Interstate 72 right outside Champaign. As I was trying to get onto that interchange, getting onto the on-ramp, trying to speed up at the same time, and we had icy rain earlier that day. I did have a spin out. Luckily, there was no one around and nothing got hurt, or there were no injuries, but it's really, black ice is really dangerous, because I until I got out of car, I did not even realize that there was any ice on the roadway or pavement surface. So it does lead to quite a few vehicular crashes and number of aircraft landing overshoots that have happened in past because of the same reason. If you look at the statistics from Federal Highway Administration, this is data that they released this particular year or this year in July. Their statistics of all the crashes across the country show that about 24% of all weather-related crashes in US are directly tied to either snowy, slushy, or icy pavements. And that 24% of weather-related crashes results in more than 1,300 people or 1,300 fatalities, and that's an annual number. So that's a quite large number. and close to about 100 or more than 100,000 injuries uh, as well. So it's obviously a topic that deserves some focus and importance because of those loss of lives as well as injuries associated with that. An example, this one's actually coming from New Hampshire. As with most states, and I checked, I know Illinois has the same system. They have a system called RWIS or RWIS, which stands for Road Weather Information System. It was deployed almost in all 50 states, or at least the northern states of US, where there's higher potential for icing and snowing related challenges on roadways. So RWIS systems are deployed across US, and they do pretty well. The example you see here is for Interstate 93. You have the image taken from that RWIS location. You also have the actual data, and I know it's hard to read because that's directly a screenshot taken from a RWIS interface. But what you are really looking at, this magenta line, is what they call grip measurement, and it's indirectly a determined level of friction that you have available on roadway. And then the system also measures all sort of parameters, the air temperature, dew point, and so on, and makes these interesting plots where it tries to show when the road is has snow on it or has some kind of wet or icy conditions. So that's all good, and that's already out there. So you might ask, why are we doing this project if this technology already exists? And the challenge with that is this technology exists, but it exists in more of a discrete spot-based measurement. So the data you saw there comes from a station very similar to the one you see here. This one's a picture taken right outside Salt Lake City in Utah, and that's a Utah DOT's RWIS station. And it has series of cameras. It has an infrared camera and optical camera, and it's measuring a location on your pavement that's between a 12 to 24 inch diameter piece of your roadway. So the drawback with these type of systems is it's linked to one location, and furthermore, it's calibrated to that location. So in other words, it's looking at all sort of image processing, spatially grayscale intensities, and then relating that back to saying, okay, this pavement is dry, it is wet, it has black ice, and so on. Great, and it works well, but again, the challenge is you are only taking a discrete point, not being able to really capture a large spatial domain. And the other challenge is it's not mobile. It's you are not able to apply it spatially in remote locations. If you wanted to determine what's happening at a certain location where you don't have this kind of station, there's really not a readily available technology out there. Now, couple that together with the use of autonomous vehicles or connected vehicles, that also, if you had a sensing system that was mobile and to some extent goes away from this need for location-specific adjustment and coming up with calibrated parameters, there's obviously would be more attraction to it. So motivated by these aspects, this particular research study was attempting to develop a sensing platform and a decision system. So there are two parts to it that can be deployed over large spatial domains. So you can deploy it over miles and miles of roadway or over your airfield where you might have several thousand feet of runway and several miles of taxiway or apron areas. So it's a system that can be deployed over these large spatial domains and have autonomy to be able to detect the presence of black ice on these surfaces. As we were developing the actual research approach in this particular study, we looked at quite a bit of literature. We talked quite a bit to people who are experts in sensing and talked to a lot of remote sensing researchers. A lot of them are also part of the big team that we have that's working on the big project as a whole. And what really we arrived at is to try to use hyperspectral signature, and I'll describe what that term means on the next slide, but to utilize this hyperspectral signature of your pavement surface to be able to detect if there's any black ice present on it. And the reasons for that, just in a very brief manner, is the sensors that we use on these are usually lightweight, so they can be easily deployed on drones or unmanned aerial systems. And as a result, they can easily cover fairly large spatial domains. The other thing that attracted us to hyperspectral signature was that there's already enough body of knowledge that shows that your hyperspectral data can be very sensitive to the moisture condition on surface of anything. So if you look at literature in hyperspectral signature, especially for sensing applications, you'll see that there's tremendous amount of literature where this technique is used for soil moisture applications. So if you're interested in farming or interested in just looking at how the soil moisture conditions are changing, this technique is often used there. So as I mentioned earlier, that I will explain what hyperspectral signature or imaging means. So just like an optical image, so where we take a picture, we always have a measurement unit or a pixel. And then for that pixel, we have intensities available within various visible ranges of light, right? We would have how much of the reflectance that we are getting from any point in this image in terms of its green color or blue color or red color or white and so on. Hyperspectral imaging is very similar to that, except instead of only capturing the visible spectrum, this image includes the whole electromagnetic spectrum, or rather most of the electromagnetic spectrum, and most of the hyperspectral images or spectral images, as most people refer to them, would include frequencies in 400 to 2500 nanometer range. So that usually includes what we call VNIR or very near infrared, which is more of optical region, but also shortwave infrared or SWIR, which is going to be between 1000 and 2500 nanometer frequencies. I just gave two examples here. Both of these are actually works done here at University of New Hampshire in the Earth and Ocean Sciences Department. One that's related more with forestry and forest ecology, where they are using hyperspectral images captured through drones, actually, much more to look at the carbon intake of different type of plant species or tree species, as well as the tree health measures, depending on how the climatic conditions might be changing. You can see another image here on right-hand side, which is at a much, much larger scale. From left to right, this image captures approximately 10 kilometers, and then top to bottom about 20 kilometers. The campus is located right around here. Actually, there's a nearby airfield that we have. And what you are looking at is ocean is onto the right-hand side. This is what we refer to as Great Bay, which is essentially a bay that's environment, which is a tidal environment. And then you have a lot of these different rivers or estuaries that are dumping water into it. And in this particular case, researchers took hyperspectral images using aircraft mounted sensor. And what they're looking at is different kind of temperatures coming from different streams, their impact on overall environment or ecology of the estuarian environment that we have here. They could also look at different kind of sedimentation or even chemical makeup in these different waters with salty versus fresh water, because once again, since you are collecting this data over whole electromagnetic spectrum, you are able to distinguish your elemental classification based on what kind of reflection you get at a specific frequency. Now, applying this technique to pavements is not new. I could find a paper as far back as 2008, where the researchers Harold and Roberts actually looked at hyperspectral imaging primarily for distress surveys or trying to relate condition of roadway to specific features on their spectral signature, and try to make linkage in order to automate your pavement survey. So it's very similar to techniques that we see when you look at automated distress survey with optical system. This one is in hyperspectral sense. So you're not just collecting data in this spectrum that ends around 1000 nanometer or 900 nanometer, but you go much, much higher. And then they showed that by doing that, you could identify some of your cracks or delaminations, things like that, that may not be readily visible in optical range. So there have been some applications to pavements, but not a whole lot. We found about half a dozen paper, a lot of them focusing on distress, some of them focusing on aging as well by using this technique. But none that were really looking at detecting surface condition as in the presence of ice or water on the surface. So the overall project or overall approach that we took here can be divided into three components. You have the lab scale evaluations where we were really focusing on, first of all, we have our proof or we have a concept in our mind. Can we prove that concept? Does this concept work that if we look at spectral signatures, can we then relate it to whether there's ice present on the surface of roadway or not? And if so, what all variables we would need to know about pavement itself in order to automate this system. Also to build a reference library, because we would like to have a library of spectral signatures of all different kind of pavements. Field scale evaluations were more to validate what we had learned from lab scale evaluations, and that's where we did deploy our sensor package on using drones and used trial pavement with black ice and so on. And then lastly, what would be the algorithm for automation? Now keep in mind, with the amount of time that we have, I'll just give you a snapshot of information from each of those three activities. There's obviously a lot of other pieces in there, but I'd be more than happy to answer any questions that you may have as we go through the presentation. And if at the end, if you want to ask more details on any specific topic, I'm more than happy to talk about it. Now from lab scale evaluation, first thing that we had to do is to come up with a method to deposit black ice onto pavement specimen. We actually also had to go through a process to determine what is a representative pavement specimen, how small or how big it can be, and make comparisons back to field and so on. But we came up with a system that uses an airbrush with pressurized air to generate fine mist for depositing black ice within a walk-in chamber, and also had to come up with a standard operating procedures for all kind of sensors. So I'll very briefly touch on that on upcoming slides. Thereafter, as I mentioned earlier, we had to do a proof of concept testing, make sure that what we thought theoretically is possible, can it be done in real life? And along that process, also identify some measures, some quantitative terms or quantitative measures that can come out of a spectral signature such that an algorithm can be developed off of them. And that way we can take out human component out of decision process and try to automate it. Within lab, once we had our proof, we also did a two-phase partial factorial testing for both asphalt and concrete specimen with all sorts of different variables in terms of the material types, the surface conditions, and so on, to identify pavement-related significant variables, but also to make some comparisons between a lab-based spectrophotometer, which is obviously your gold standard when it comes to getting spectral signatures, versus a UAS-based sensor, which had to be a lightweight sensor that can go on the drone. So just on that first topic, the setup that we came up with, as I mentioned to you on previous slide, is an airbrush-based setup that runs off of compressed air and obviously with water as a media to deposit black ice. There's just a picture of one of the trials, but we did quite a few trials in order to really make sure of two things. One is that we are getting uniform coverage of black ice on specimen, and also that we are getting uniform thickness and can control thicknesses of these different depositions. And the way we did was really by applying black ice on white media using food dye, and then we would do all sort of optical analysis on these depositions to make sure that we are getting uniform coverage and also be able to relate to the thicknesses that we are getting. So that was an effort in itself, but I don't have time to go through through every detail on that. Sensors that we use for spectral measurements. In lab, we used a handheld spectrophotometer. This is a sensor, as I said, this is what is considered as a gold standard when it comes to hyperspectral measurement on any surface. This particular device is quite large. Just to give you a perspective, this just the power supply and the measurement system for this particular spectrophotometer, that's about the size of a large backpack. So, and it's quite heavy. I mean, just weight-wise, this whole thing is close to about 30, 40 pounds. So we cannot expect to deploy that using drones, but it forms as a really good basis for our measurements because it gives us a very detailed information. The resolution is very small on it, 3 to 10 nanometer, and there's about 2100 bands along which it measures the information. Now, compared to that, the sensor that we used in this study that was mounted on drone is the one shown here. It's quite small. Dimension-wise, you're looking at about 1.5 inches by 1.5 inches by 1.5 inches. So it's really a small cube that you can easily put on a drone. Obviously, it comes with limitations that it measures a smaller range along which it takes measurements, and it has fewer bands, so it has 270 bands of measurement. Also, Adam, working together with our undergraduate student, Genius, came up with this very nice linear stage because the drone-based sensor is a line scan, so it scans one line at a time. And so in order to scan our specimen, the specimen had to move. So they came up with this linear stage they just assembled in lab with a stepping motor to get the measurements. Now for the partial factorial study, the design considered really 5 factors, which were material types. And for each material type, we had its own baseline. So for asphalt and PCC, granite being the aggregate geology as a baseline with limestone and basalt as alternatives. We had the gradation alternatives in terms of nominal maximum aggregate sizes, 9.5, 12.5, and 19. Also surface conditions. So you have your new condition as a pavement, but you also have different wear levels, and socket, which is not really, it's synthetic because usually we don't have socket condition, but that kind of serves as the other extreme end as opposed to new condition from wear perspective. And then lastly, we have grooving. So with grooved and non-grooved condition, because a lot of airfield pavements, actually all runways in US will be grooved because that's FAA as well as TOD requirement. So very quickly, just a couple sample results, and these are just baseline measurements. So there's no black ice here, but I just wanted to point out as materials change, the spectral signature also changes. So what we are looking here is the amount of reflectance that happens at each of these wavelengths. And once again, visible wavelengths would be much more in this range versus everything here is not really in the visible range. So you won't capture that with optical type of system. But what we can see in this example is you have your black line, which is granite. Then diorite, which is very similar to granite. It's granite's cousin. It's also a siliceous-based aggregate geologically. And then you have your limestone, which is shown in green line. And what you can see here is that for each of those 3 type of aggregate geologies, the signatures are a little bit different. Obviously, diorite and granite does not have too much different because chemically they have similar makeup. But nonetheless, what's also interesting is that the features are not really that different. In other words, you could still see the features that are present in these aggregate geologies as in limestone. It's just that their magnitude might be different. So why is that important? That's important because if we are going to use, again, an automated system that is specifically looking at features, what this tells us that the surfaces are still correlated. We don't necessarily have to have a different data set or different procedure when we are using granite as opposed to limestone as our base material for our roadways. And another example here, there's again for dry specimen, there's no water or ice, but this one is reflectance showing on concrete specimen. And the main difference here between these 3 type of concrete specimen is you have 9.5 millimeter aggregate nominal max aggregate size, 12.5 and 19 millimeter. Keep in mind this with concrete, so we did grind these specimen surfaces, because if you don't, then you always have cement paste on top and they'll all show same way. But if you look at these again in terms of the aggregate size, the actual reflectance values change, but once again, the features that we are looking for, where you have peaks and valleys and how much they change in relative sense, they did not really change that drastically. So going to the proof of concept evaluation. So these were the main hypotheses that we were evaluating. First one was, does a dry pavement surface versus the one with water or ice have difference in spectral signature? Second, as water goes or moisture goes from water to ice phase or from liquid to solid phase, does that impact the spectral signature? Does temperature have an impact on just the dry pavement surface? Because we don't want any false positives where it's just dry surface, but because of the temperature change, the spectral signature is changing, and now all of a sudden we are thinking there is ice there. What are some of the most important features that we can use to build a decision system? In other words, what are specific aspects in those spectral signatures that can be adopted to build a decision system? And those were the four primary hypotheses that we are trying to evaluate in the first part of lab evaluation. And I'll show you some results. First one, obviously showing the proof of concept. The second one showing that with spectral signature, one could also look at the thickness of how thick the water or ice might be on pavement surface. So just one set of results here, and what we are looking at is in this particular set, we have our control specimen, which is dry, and we have a sample, which we call damp here, but it's the one with black ice deposited on its surface or black ice applied on its surface. And then both of those are going through the cooling cycle. So blue and red line are just showing the black ice specimen versus dry specimen. And then the black is just showing the air temperature inside our chamber. And then we have periodic measurements, and that's a little bit hard to see, but these are faint yellow boxes that you see where we took periodic spectral measurements on the surfaces of these specimen. We also had all kind of measures with respect to how many points we take measurements and how often and so on. So that's all based on repeatability and statistics. But we took enough replicate measurements to make sure that the results were giving us high confidence. Also, you can see two temperatures that are indicated here on this slide. Obviously, 0 degree is well known in terms of when you have phase transformation, water going to ice, but we also identified negative 3.58 as a temperature, which gives us 95% confidence interval in terms of temperature that all moisture on surface of pavement is frozen or is in ice state. That comes from a couple of different things. It comes from just the variability associated with our measurement system, with the thermal imaging, plus the checks that we do in terms of whether there's really in ice form versus liquid form as we take these measurements. So at the end for our system, what we ended up with based on all the statistics is that minus 3.6 is where we get to 95% confidence interval that any surface moisture should be in form of ice. So this first result is just showing dry specimen. There's no water applied on it, and you can see that nothing happens, which is good. So in other words, if you look at the normalized difference, which is difference in reflectance between specimen at room temperature in dry condition versus the one that goes through the cooling effort, nothing changes. That means that at least we will know when a pavement is dry, and we won't have to worry about it telling us falsely that there's moisture present on it. On the other hand, when we look at wet specimen or a specimen with moisture present on surface, we could clearly see that it has a very different reflectance pattern when it's normalized against the dry condition. And also we could see that as temperature drops, it evolves. And that's clear in this plot where this is the wet condition, these are the ice conditions. The last two measurements are both below 3.6 degree, negative 3.6 degree surface condition. A couple things that we can right away see is there's an offset. In other words, the reflectance is changing as water becomes from water to ice. The other thing that's also interesting and gives us good confidence is if you look at literature and if you look at just spectral signature of water, just because of its molecular makeup and how that makeup changes as water goes from water to ice, and the angle between hydrogen and oxygen, the bonds changes, you see a 50 nanometer shift, and that's well documented if you look at textbooks on spectral images. And we were seeing the same thing here, seeing exactly 50 nanometer shift in these features, the peaks and valleys in what's referred to as shortwave infrared range or SWIR range. We did additional experiments. This time we also started looking at what happens as the thickness of that black ice changes. So damp is where we have the minimal thickness. Typically this would be in terms of millimeter, you're looking at about 1/10 of a millimeter moisture film, all the way up to about 3/4 of a millimeter. We impose these same samples or same kind of samples through a cooling cycle, once again, as we did earlier. And when we look at the results, once again, the black ice one with very thin layer of moisture, you could see that offset going from wet to frozen or ice to over condition. You are seeing the offset. It's hard to see because I have 4 plots here, but you could also see the 50 nanometer shift. It's a little bit more clear in case of slightly thicker ice layer with 0.25 millimeter. Once again, there's still an offset in the visible range, and there's a 50 nanometer shift that we saw earlier. Now, the most interesting thing that we found with these results is that when you go to these thicker films of water, above about 1400 nanometer wavelength, we saw a complete attenuation of signal. In other words, there's no reflection happening, and that was, to us was a new finding. We looked quite a bit at literature. That's not something that's really out there or published spatially for pavement surfaces. So that was kind of interesting to see that once you go above a certain thickness of water film, it totally attenuates your signal in the higher electromagnetic ranges. Now, based off of all kind of analysis, we dumped all of this data into different kind of statistical modeling software. We use software called JUMP, if you're familiar with that. But at the end, what we came up with 4 quantitative indices that reliably pick up when there's moisture present on the pavement surface versus when it's dry, and also what happens to specific features or what happens when that water transforms from water to ice. So the first 2 are really focused on looking at that offset in the visible range, and that really tells you wet versus dry pavement. There's also total absorption. So the absorption, you see more absorption of your signal when there's water present on surface versus dry. And then the other 2 are more tied to the formation of ice, and that's looking at what happens to you when you get the feature that corresponds to your maximum absorption. And again, these black and red lines are showing where your features are in terms of peaks and valleys in your data. There's also average max absorption, which is similar to the wave max absorption, but it's over the whole range. But in any case, the bottom line is there are 4 mathematical measures that any of these curves can be distilled into. With that knowledge, we did, as I mentioned earlier, some partial factorial testing at 2 different phases. Phase 1 was really to look at those factors that you saw on a previous table. And I'm just showing one technique that we used, the correlation matrix, to identify whether the signatures are correlated or not. And as you can see in this example, irrespective of the aggregate geology, the signatures are actually correlated. However, when you look at the black ice condition, all of a sudden you start to see impact of the geology in terms of what happens to your spectral signatures, which is good and bad news. It's good news because there's clear distinction from dry condition, but at the same time, it also means that we need to know what was the geology of a specific pavement that we are surveying or sensing. Just another example of that same partial factorial effort. Here we are looking at dry pavement and its spectral signature. There's not normalized difference. This is as measured. And then the red one is showing when you have a no wear to that pavement surface but black ice. And then the green one is showing when you do have wear to that pavement surface. And it's a little bit challenging, but once again, if you look at specific features, the water-related features are present in both of them, irrespective of the wear. Their amount or the degree of reflectance obviously changes. So what did we learn as lab scale testing effort? And sorry, I'm trying to rush because I am aware that we are running out of time. I should be done in about 5 minutes, and so we should have plenty of time for questions. But the main things that we learned here were that when moisture is present on the surface, it does reduces reflectance in terms of spectral signature, and the amount of that reduction is sensitive to the state of water, which is good news because we should be able to distinguish between wet pavement and iced over pavement. And even more, we should also be able to get some insight on thickness of that film. Why is that important? From practical perspective, that's important because that might control the type of de-icing chemical or anti-ice system you may use and how much application rate you would need in order to get rid of that ice on the surface. We also learned we also confirmed that 15 nanometer textbook offset that you have with water as it goes from water to ice is present when you have same effect happening on pavement surface, at least when you have thinner films of ice. When we did all the analysis, we were able to show that when you have dry asphalt pavement surface, the signatures are correlated pretty well, and that's good because that means we need limited amount of information about the existing pavement in our automated system, and we don't have to have every pavement surveyed up front. We did see though that the reflectance value do change when you have black ice with degree of surface wear. So that if you knew that information, at least knew age of pavement, that would improve the reliability of your prediction. On concrete side, the only variable that continued to show a strong effect in terms of both dry and iced over condition was nominal maximum aggregate size of concrete, or maximum aggregate size of concrete, I should see. So that's information that again would have an impact on outcome. And then at the very end, the similarity and dissimilarity of spectral signatures do depend on surface wear, and I already mentioned it in the earlier point there. So now let me very quickly talk about the field testing that we did. And once again, you can see Adam there. That's our bigger drone. That's a smaller drone that we used in this particular study. It's very deceiving picture because the temperature outside when we are doing this is about 15 Fahrenheit. It looks nice and bright and sunny, but it was extremely cold and also quite breezy. The platforms that we used in this particular research, two drones, these are fairly large size drones, so these are not typical drones that you can go and buy at a store. Both of these have a quite high payload capacity, so their takeoff and landing weights are more, I mean, the published ranges are more in 30-pound ranges, and they obviously a lot of that weight goes into the batteries, and then rest goes into sensors. This picture of Professor Palace, who is talking about the drones that we used in this study. One is a quadcopter, and the other one is also quadcopter, but with 8 propellers. You can also see the sensor packages on them, and I'll talk about them very briefly on next slide. So on these drones, we have really a 4 set of sensors. We have hyperspectral, which I already talked about, but on these, we also have LiDAR, and they are fairly high resolution LiDAR with 2 to 3 centimeter accuracy at 100-meter distance. These are active sensors, so they have their own laser source to take measurements. There's also obviously the navigation system and the GPS associated with that allows us to really do all the data processing and generating data cubes for every flight that we do. And then there's a thermal camera as well that we put on these, that can go up to -25 C and give us a very good quality thermal measurement. The field experimentation, everything that we conducted is working together with University of New Hampshire's Facilities Management and Parking Services. We were able to identify a parking lot at a center that is our Advanced Manufacturing Center for UNH. So not very unlike ATRL, it's a facility that's off campus. And as it happens, they have this lot of parking lots around the building, and one of them was the one that they could easily cordon off or close off to people, and they did that for us. We asked them not to de-ice it because we wanted black ice to form, but at the same time, we wanted them to plow it, and they would plow it after each snowstorm. We had to come up with technique for applying black ice in the field. And you can see picture of Gerius, who's an undergraduate student who has been working with us. So we had to use this fine misting setup with a constant flow rate so that we can estimate the thickness of the film, and also come up with a spray pattern with how many passes and so on to come up with a representative area that we would evaluate. Now I'm just going to show you results of one of our final flights that we did before we had COVID and things shut down. So this was taken in March. We plan to do hopefully one but few flights this winter as well. But you can see the setup, and I apologize, it's a little bit smaller. But what you are seeing is two areas of black ice deposited. You have what we call light versus heavy black ice, excuse me. And that's really function of how many passes of application we do. We also have our control area where there's no moisture present. Since parking lot has its own gradient, we were able to set up these fences and make what we call graded ice. They are great because it allows us to see how the spectral signatures change over thickness of moisture. And then since we are out there and we had access to a lot of snow, we also added one more section, which was just to look at what happens when you have images with compacted snow, because people often find compacted snow to be quite slippery. So that's not something we did in lab, but since we were doing field evaluation, it doesn't add much more extra work to have another evaluation area. We added that as well. Just looking at spectral normal difference. Now, one thing to keep in mind, and you might have picked up, the sensor that we fly on the drone is limited in terms of the bands that it captures. It does not go into that SWIR range. But the good news was that we checked all of these data by also doing handheld AST measurement with spectrophotometer, and there's very good agreement between the two. So it shows us that at least both sensors, the one on the drone and the handheld, were agreeing. And just jumping to one set of results for the graded section and also the light and the heavy black ice sections, we saw that optical region offset was holding true. We were still seeing offset when there was moisture present or ice present. And we were also seeing specific absorbance features that were tied to the thickness of that layer or thickness of ice. So it was being sensitive to that thickness changes. So using that information and obviously a lot of other data that I didn't have time to show you today, for now we have come up with this decision process. Keep in mind, this decision process does use surface temperature as an input. You don't have to. If you had a different hyperspectral sensor on the drone, that could go into the SWIR range. But since we are limited in this study up to 1000 nanometer, we felt that in order to have higher reliability, it's good to also have a thermal information on surface, which is easy to get because thermal cameras are cheaper and you can get them fairly easily. But the overall process relies on that offset in the optical region to detect whether a pavement is dry or has moisture present. And then looking at spectral absorption, you can determine whether you have, for now we went with a binary system, a thinner film of moisture versus thick film. And then lastly, using the 95% reliability temperature threshold of -3.6, you could determine whether you have wet surface ice present or likelihood. So last slide, summary. what we saw through this project is that the spectral signature can tell you whether pavement surface is dry versus wet or has ice on them. We did come up with 4 absorption indices, 2 of them telling us whether it's wet or dry, and 2 of them giving us some insight on the phase of that moisture, whether it's frozen versus liquid. Those 2 that tells us that were outside the range of the drone flown sensor in the study. So for now, our recommendation is based on thermal data together with the first 2 indices. And the offset in the visual range as well as total absorption together with thermal measurement can come up with the system as you saw in previous slide. Obviously, we need to do more field testing for continued validation and calibration. And one thing that we are also doing is developing a library with idea that then we can apply machine vision in order to build more autonomy into this decision system. So some other areas that we are working on or planning to work on are shown here. I won't spend time on it. I'd rather have time for questions. So Javier, I'll stop here and would be very happy to answer any questions or listen to any comments that people may have.
Right. Thank you, Professor David, for the presentation. We're going to take just 15 seconds to move everybody to promote everybody to panelists. It's an automatic thing, so you guys are just going to be moved so that we can have a more fluent discussion. Give me just 1 sec. All right. So you guys can either use the chat to say if you have a question or raise your hand and I can let you ask your questions. I did have one for you, Professor. I'm curious to know, how did you measure the thickness on top of the specimens when you did the lab testing? And then if you could recap on how this thickness affected the reflectance, but before it attenuated it, what happened there? It wasn't very clear for me.
So that's a very good question. And there are different ways that you can get thicknesses on this. I mean, okay, when you have a nice cut face, it's pretty easy. You can use any kind of thickness measurement system to get that. In our case, we were mostly relying on volume-based measurement to get the thickness estimate. So if you know your application rate with respect to your surface, you are trying to estimate the thickness on the basis of that information. So we are really relying on the spray rate that you are doing and how much water is going through the system. Now, for lab experiments, it's pretty straightforward because, as I explained, what we did was we really had a setup where we could pre-calibrate these air guns or I'm trying to remember the exact name, what we call airbrush system, where we know how much water it would deposit on the surface of your particular specimen, depending, and we run them at a constant pressure with constant volume of water and everything else. So that's how we are getting the water quantity estimate. In the field, it's a little bit trickier because we are not able to have that kind of very controlled setup on a larger domain. So we still use the flow rate. So while we tried to be doing very good estimate of it, and that's why I didn't put exact thickness values in the field results, but rather go with what I call light versus heavy. But in terms of estimate, we were targeting something that would be about 0.3 millimeter and 0.7 millimeter of thicknesses. Now, your other question was with respect to the attenuation, right? Where you could see here that the signals were getting attenuated once you get above a certain thickness of water. And again, why that happens, a lot of it has to do with just the absorptivity of water. When you have electromagnetic measurement coming at certain wavelengths or above certain wavelengths, I should say, And when water thickness increases to above a certain threshold, then it just absorbs the signals and doesn't provide any more reflectance. And that's what we were seeing here. I don't know if that helps answer your question or not.
Yes, it does. Thank you.
Okay.
So we have Anjali. You can unmute and ask if you want.
Hi, Eshan. It's nice to hear from you and really nice work. I was curious if you could comment on the outlook for the deployment of this platform. Because for instance, for a roadway network will be pretty vast. So how will you prioritize, the spatial paths for the drones versus what about using discrete sensors that have metrics of, okay, here, the current conditions right now will be ideal to form black ice?
Yeah, no, thank you, Anjali, for your kind words, and it's a very good question. So what I'll say first is there's actually very good work that's already done right now, not by us, but others, that have looked at when you have these road weather information systems or discrete measurement locations, what are your best algorithms with respect to taking data from that network together with your meteorological conditions to try to identify in a probabilistic sense where would be high chance for icing to happen. So I would imagine that we would not get rid of those, but rather use those discrete sensors as more of a trigger to determine where you should deploy something like this. The second thing I'll mention is, to me, the first and most no-brainer application would be on the airfield applications because of two reasons. A, you could get, I mean, obviously you would need all sort of permissions and other aspects. So anyone who's gone through to drone operator licensing would know what kind of conflict points may exist between aircraft operations and drones and stuff like that. But there it makes a lot of sense because there's already fairly good meteorological information that you have on any airfield, and a lot of times they would also have existing sensors in place where this could then supplement that. Now, purely from why U.S. Army Corps of Engineers is interested in this research, then the application is a little bit different. In that case, you are more concerned with if you have to have movement of troops in remote areas and you cannot be there, or you are planning a mission and you want to assess what the condition is before you send out a troop carrier or for airfields or send out any kind of other vehicles, then you can use this as a kind of a planning tool that goes up front beforehand. But the question is very good, and again, we see this as kind of enhancement to the discrete locations, and be able to use the information from discrete locations to trigger where you would send out such a system.
Thank you. Just one question. It'll be quick because I know that Puneet also wants to ask a question. Are there certain conditions that would affect the fidelity of the sensors on the drone, and what will they be?
Absolutely. So obviously, while as robust as these drones are, if you have adverse weather conditions, I don't think you'd want to be flying them. So that goes without saying. That's the biggest one. There are temperature restrictions, but the good news is you can really buy, especially for spectral, hyperspectral sensors, you are really able to buy pretty much any temperature range that you are interested in. The one that we have, you'd not want to go or fly it in conditions below, say, -25 Celsius, for example. So it would not work in Arctic regions if that's where you're interested in. But that same company makes other sensors that you can use in those other conditions. The one last restriction that may or may not be there, once again, depending on the type of sensor you use, with some of these spectral imaging conditions, you would need a light source because that's what is reflecting off of it, right? So if you are trying to do analysis in some different conditions, that would matter. And once again, there are solutions to it. You have active sensors or LiDAR type of sensors where you might have a laser-based light source that you are able to use so there are restrictions, but there are also solutions with it. But the biggest one I see is being able to take measurement in inclement conditions. That's where, again, discrete sensor would work great. But when there are inclement conditions, people are aware that there would be icing. So this is more for when you have mechanisms like freezing fog or refreeze of molten melted ice or snow, or drizzle, those kind of conditions. So hopefully that provides some insight there.
Okay, we have time for one more question. I see Puneet has his hand raised. Go ahead, Puneet.
Thank you, Javier. Thank you, Professor. The way it was really interesting work, and thank you for the presentation. I have one. I have one question. So I've been into the same situation as of yours. My car kind of flipped around, and it was next to a trail. So I wanted to know, like, what is the what should be the thickness of ice to be dangerous in terms of black ice?
Yeah.
And I have a follow-up question. The second question I have is, like, if you're trying to use this technique, especially like in the rural areas, like how would it be like because in rural traffic you don't have much traffic, so how would you monitor that? You know, how frequent you should do it?
Yeah, so both very good questions. So regarding the thickness side of it, there's actually, interestingly, not a whole lot of literature that you can find that will tell you exactly at what thickness threshold pavement starts to get slippery. One thing that we are planning to do during this winter's field testing is we are actually going to do friction measurements on pavement. So that will give us information on it, also measuring how the friction levels are changing with different thickness deposition. The number that I've seen most frequently is again, it seems that until you're about 0.2 millimeter, less than 0.2 millimeter is typically not included in most of the studies, and partly it's also because it's very hard to deposit something naturally also below that range that would not break down under your vehicular conditions with the macro texture of pavement. Your second question with respect to the rural versus urban, and rural areas, especially remote areas, once again, the impetus for that in this particular study was tied more to movement of troops or movement of forces in rural areas. In terms of traffic or transportation application, I think it's going to have to rely a lot on prioritization, right? Where are the priorities where you need to deploy? Now, one thing that we are working on is taking the same kind of setup as we have on drone, but also extending it to as a sensor package on vehicles. And that is really where I think the rural application is going to be, because the analysis side stays same. It becomes something that you could even have on snow plows. And by doing that, as you are plowing your roadways, you are constantly collecting information. And that's where I see the application going into more rural areas with same technology.
Thank you so much.
Yeah.
All right. Well, we don't have any more questions and we're about on time. So thank you very much, Professor Dave. And thank you everyone for attending. Next week, we have Professor John Harvey at the same time. So please join us. Goodbye.
Thank you very much, Javier.